Hello, Dr. Prakash. As you know, my name is Tom Hansen, and I am a member of the Alkaline Surfactant Polymer Water Treatment Facility project for the CBE 4497. I wasn't at the capstone presentation, and so instead I'm sending you a video of my presentation of the unit I designed, the weak acid cation unit. So, the purpose of the weak acid cation unit is to soften the water through ion exchange. In this unit, hard water comes in with a concentration of calcium and magnesium at around 0.005% mass fraction, and it leaves at around 0.002% mass fraction. There are three steps of operation in this unit. There is a steady state, where, as I've just described, the harder water comes in and soft water leaves. In this operation, hard ions, calcium, magnesium, leave the water, and soft ions from the resin, sodium, enter the water. The next step is hydrochloric acid regeneration, where hydrogen enters the resin and the calcium and magnesium ions leave the resin. And the final step is sodium hydroxide regeneration, where sodium replaces the hydrogen in the resin. Now, on the next slide, there's a brief overview of our design options, or our alternatives considered. So first off, we looked at two different types of technologies. The first is a weak acid cation unit, and the second is a strong acid cation unit. We decided the weak because the strong acid cation unit would not operate at the conditions we desired. And the most specific of this is that we expected total dissolved solids coming in at higher than 3,000 milligrams per liter, and a hard acid cation unit simply does not operate at these conditions. We had to make this decision, although hard acid cation units are used more commonly in industry and are therefore cheaper, but it just wouldn't work for our function. Now, once we had selected a weak acid cation unit, we had to choose what type of resin to put in. And so there were two dimensions on which we could make a selection. The first is the physical structure, and that included macroporous or gel resins. And the second is the chemical structure, which was styrene or acrylic. Those were our two options. We ended up choosing a macroporous physical structure and an acrylic chemical structure. These were both chosen for their increased resistance to fouling, specifically organic fouling in the case of acrylic structures. Obviously, that's very important because there will be lots of organic or hydrocarbon in this system. We chose resistance to fouling as our primary design factor because this unit needs to operate consistently, or else if it goes down, there can have strong ramifications on the production of the reservoir, and it can severely limit the plant's effectiveness. On the next slide, we have a brief overview of the chemical reactions that happen in this unit. And I've kind of briefly described them as I described what leaves and enters the resin. These reactions are driven by the resin's affinity, which in normal situations is driven by the size of the molecule and the polarity. And so the resin has a stronger affinity for larger molecules and more polar molecules. So during steady state operation, the sodium is less desirable by the resin because it's both smaller and is less polar than the calcium and magnesium ions which enter. In the second regeneration with the sodium hydroxide, sodium is selected for over the hydrogen because it is a larger molecule. However, during the first regeneration, the opposite occurs. And this occurs because during highly acidic concentration, the resin's affinity switches. So it chooses the hydrogen over the larger sodium molecule because the hydrogen is smaller. On the next slide, we have a brief overview of some of the design challenges we faced. One thing I've already talked about is resin contamination. Again, we need this plant to operate efficiently and reliably. So we chose the macroporous acrylic structure. And the second thing, another issue is how to identify resin efficiency. There are a whole bunch of things which can limit the resin's efficiency, whether it be sodium ions in the incoming stream. There's always a hardness slip of some level. And so we had to design for those and calculate what we expected those to be. Our calculation method roughly used a lot of empirical correlations for weak acid cation units, but roughly what we did is we found the surface area we required, the volume we required, and then made sure that the hardness slip, pressure drop, volume expansion, temperature change of this unit would not limit the safety or the function. On the next slide, we have a brief overview of, the actual unit. The unit will be made out of stainless steel. Fiberglass would be cheaper, but it can't withstand the pressure that this unit operates at. The piping and instrumentation is also stainless steel, although all of the internals will be covered with rubber to avoid any corrosion, or to limit corrosion. The unit will cost just over $700,000, and there will need to be two units. So while one is being regenerated, the other will be in steady state operation. And then that's how they'll run on 12-hour cycles, and so that's how we will have consistent product. On the next slide, we have a brief overview of the instrumentation and control that this unit is using. We have 4 different types. The first is pressure. So pressure is used on the incoming hard water stream and the backwash stream. These were chosen pressure because that's the greatest risk with these streams. And there's also a pressure transmitter based on the unit, so if it's linked to a release valve. So obviously if the unit pressure gets too high, then it'll signal the release valve and that'll be released. The next control we have is temperature. Temperature is controlled on the unit, and during the regeneration, there is expected to be an increase in the temperature because they are exothermic reactions. However, it's expected to increase roughly 2 degrees Celsius over 50 minutes. So we don't think this is a threat at all, although we obviously have put in the necessary safety precautions. If the temperature reaches too high, the incoming regeneration stream will simply be shut off. Finally, we have flow controls and concentration controls, and these control the incoming regeneration streams. So concentration controls the actual chemical, so be it hydrochloric acid or sodium hydroxide, and the flow control controls the soft water that is produced from the black that it is mixing with. And so between these 2 controls, it ensures that there's the right amount of regeneration fluid entering, and the regeneration fluid is the right concentration. Thank you very much. I hope that this is what you were looking for, and I hope you have a good summer.